Okay, so let's continue and let's start now to learn about some unsupervised machine learning methods, and we'll see hierarchical clustering, k-means, and sort of component analysis, how we can use these on our logical data sets, again, to produce some visualizations, but the idea really is to understand the data and possibly calculate new metrics that we can then use to annotate additional normalizations or additional visualizations. So I'm going to open the script here. And so let's start maybe with hierarchical clustering. And so let's say we have 5 points, and I represent them here in this 2-dimensional data. Let's say we have points 1, 2, 3, 4, 5. The way a hierarchical clustering works, the first step is always to calculate a distance between all these samples. So here we have 5 samples, so that would give us 5 by 5 matrix with all these distances. And then the first step is to group the 2 samples that are closest to each other based on that distance that we use. And so in this case, 3 and 5 are close to each other, so we would then group 3 and 5 and make it a new group and update our distances, or pairwise distances, this time to calculate distance between 1, 2, and 4, and then kind of centrate the center of this new group 3 and 5. Okay? And so the next step would be to combine, maybe based on my plot here, this 3, 5 plus 4. Next step would be to combine 1, 2, and the last step would then combine all the samples. And typically the way this is visualized is using a tree-like structure, dendrogram, where leaves, these dendrograms are all individual samples, and then we start to combine them based on this clustering result. Okay, and then we had 1, 2, and eventually grouping all the samples together. And the length of these branches here, so we have an axis here that gives us the height of the tree, and the length of these branches here is proportional to the distance that we calculated. And so we can do this in R using a set of distances, set of functions. The first one is the dist function that will calculate the distance, and then we can feed the result of this distance into the hclust function to do our hierarchical clustering. So I'm going to use here some real-life data sets to illustrate these different methods. And the package control of data provides this data set from Mulvey 2015. And I'm going to, so that's a Zen set. So these unmixed data containers that contain all sorts of information. So we have quantitative data for 2,337 proteins and 18 samples. And if we look at the experimental design here, so we extract the sample annotation So here is the sample annotation. And so here are the sample names. So we have replicates. These are triplicates. So we have one set for replicate 1, one set replicate 2, and one set replicate 3. And then we have different time points. So this studied the development of stem cells. So we have time point 0, 16, 24, 48, 72 hours, and then the Zen state that corresponds to the fully developed cell line. So 6 time points, all replicated, repeated, measured repeatedly in triplicates. This gives us 18 samples. Okay. So the first thing we need to do is to calculate the distance between all these samples. So we can, for that we need the quantitative data that we can extract with the EXPRS function. So here all this quantitative data for the 2,500 or 3,000 proteins, and here are the different samples. Okay. But what I will want to do now is to calculate, and we want to do the clustering, my hierarchical clustering on my samples. Okay, bear in mind that all the techniques that we're going to see, we can use them to study the patterns in our samples here or in our features. And some of the examples that we'll see will do one or another. So here, EXPRS, and I extract the quantitative data, but I'll need to transpose this data so that I don't have it features by samples, but I want to have it samples by features so that I can calculate the pairwise distances between all my samples. For example, here the distance between my 0 hours and 16 hours for replicate 1 is 5.23. So by default, that's the Euclidean distance. Between 0 and 24 hours, 5.9, and so on. So I'm going to call this, for example, D. So here's my pairwise distance. So it's an 18 by 18 matrix because I have 18 samples. And then I can feed this distance immediately to the hclust function to generate a specific type of objects. Yeah. Okay. This object that stores the clustering results. That is presented here. Okay, so number of objects 18, that corresponds to our 18 samples. And I can simply plot this hierarchical clustering objects with plot HCl. To produce this representation. And so we see here that we have all the triplicates or final state, the Zen state, that group together, that are apart from all the other ones, and then we see a pattern here where we have one large cluster with the 0, 16, and 24 hours, and then another one here with the 48, 72 hours. So based on this kind of preliminary analysis, we have kind of three nice groups, one corresponding to the kind of 0 and early time points, and then middle time points, and then the final stage. Let's go. Again, first step is to calculate distance, and then feed that distance into the hclust function, and then eventually we can plot the function, plot the tree with plot. So that might be what we want, and we might want to stop there to get an kind of overview of the relationships between these samples, but sometimes what we also want to do is to infer cluster membership from this tree. And we can do this with the cut tree function. So we need to pass the actual clustering that we produced And then we can define clusters. Either say, well, I want to define my clusters based on the height. Okay, so for example, if I say I want to cut at 15, so let me first add a horizontal line here. Right, horizontal line. Okay. So if I want to cut my tree at a height of 15, I can define this here. And this will now return the cluster membership of all my samples. So my sample 1 here corresponds to the 0, 16, 24, here another 0, another 16. So my cluster 1 has been arbitrarily labeled as this one. My cluster 2 contains the 42 and 72 hours, which is this one. And then my cluster 3 contains the Z samples. Alternatively, I could also say, well, I want to cut my tree so that I end up with 3 clusters. And same thing here. I would not get the height, but the software will automatically identify how to cut to obtain 3 clusters. Okay, so a little exercise for you. You could using the same data set. If you have another one, feel free to use another one. But what would be the clustering that I would get if I used, if I wanted to have 5 clusters? How would my clustering result be? And how could I find, based on this hierarchical clustering, the 5 possible clusters to identify? Now there is one really critical step here, and that's the calculation of this distance. That's extremely critical, and to give you an idea of how the distance can be critical, there is this little matrix here that gives us the expression for 3 genes in 5 samples. And then we can visualize it. I need to take transpose. Sorry. So here we are. Gene 1 in black, gene 2 in red, and gene 3 in green. Overall 5 samples. And again, this would probably not be the right type of visualization if we wanted to look at this, because this, these are independent samples. If it was a time course, then this would be the appropriate type of visualization. But here I want to highlight the fact that the profiles of these genes, and we see that 1 and 2 here have very, very similar profiles, but on different intensities, whereas 1 and 3 have different profiles, especially here at 4, 5, but they are much closer in terms of range and intensities. And so to illustrate this a little bit more, let's load a package called BioDist. Allows us to do some kind of different distance calculations, different types of distance calculations. And for example, the Euclidean distance, that does exactly the same thing as the dist function that we used before. And so here we go to feed this immediately into H class and plot it. And so here it's what we get. We get the clustering gene 1 and 3. And indeed, there is a small distance between, relatively small distance between 1 and 3 here. But now let's do the same thing, but instead of calculating the Euclidean distance, we're going to calculate a distance between based on the correlation of these, and suddenly we see gene 1 and 2 that cluster together because indeed they correlate extremely well. So this is to show that in clustering in particular, but in general, many different algorithms that we look to use, exactly how we we process our data, what kind of assumptions are made about the data will influence our results. And certainly when we have thousands of genes that we look at, we want to have a big picture. There is no way we can start to pick up on cases like this. And so typically what we would want to do is to scale our data. So here is, yes, of course.
So what is the library BioDist?
So BioDist is a package, so library loads that package, okay? So BioDist is a package that provides off-the-shelf distance calculations. So you calculate a Euclidean distance, which is the same thing as dist, dos, and above. And core dist calculates the correlation between these two, between the features, and then uses that as a distance. We could also do it manually, and there are probably many more in BioDist.
So this could also be like using the dist function.
Yeah, so this should be exactly the same result as the dist function. If we wanted to calculate something like this, we would use the core function to calculate the correlation. So here, so very often what we want to do is to scale, normalize these data before doing any analysis. So here, I calculate my row means that I subtract immediately from the actual intensity. So this will be 1 minus the mean for gene 1, and 5 minus the mean for gene 2, 1.6 minus the mean for gene 3, same thing for my other samples. And then in addition, I'll want to divide this by gene filter rho SDS. So rho SDS is a function from the gene filter package that will calculate standard deviations over the rows of matrix. So we have row means, row median, row and call sums, and so on in base. Or if we want to have the equivalent for standard deviations, we can use this function from gene filter. E. So these would be my scaled intensities. Let's call this E2. And plot T2 and I both. And so here is our scale data. Now we see that 1 and 2 perfectly overlay because we have removed the effect of the intensity. Okay. And now we can use the Euclidean distance on this data, and we will see indeed that 1 and 2 cluster together. And so the type of distance that we can calculate will have an effect on the data. But here I used different types of clustering methods. So exactly how are we going to cluster to partition these data sets? And this is controlled by the method argument to h-clust. And again, as you can see, this can have effects. So I think generally complete clustering method is what is used and probably works in most of the cases. And of course, trying fancy or different methods is not always useful because we have some expectations when we look at the graph. And if somehow only there is some benefit of keeping defaults so that we know what to expect when we look at the graph. So changing the parameters left, right, and center is not useful. We need some consistency to be able to look at these graphs and make some interpretation. But anyway, it's important to know that we have parameters that will influence our results. So here's another exercise. And this one uses still a data set from raw data, but one that is called Hyperlogic 2015. So 5,000 features, 20 samples. And so I'm just going to suggest that we use a subset of this data set. I'm going to I'm going to tell you in a second what subset we're going to use. Set Hyperlogic, and let's call this HLM. So dimensions, Hyperlogic, and dimensions HLM. So we'll take just on a fifth of the features of the proteins of this of interest, and the difference is the following one. So this is the table of feature metadata. So these are the protein identifiers that we have in this data set. Protein description and additional protein-specific information. And there is one column here that gives us the subcellular localization of these proteins. So for each of these proteins in the data set, we have recorded its confident subcellular localization. And so we have here ER Golgi, mitochondrion, extracellular matrix, nucleus chromatid, and so on. And for 4 out of 5 of these proteins, the localization is on them. And so my suggestion is to focus on those that have a localization that is known, and this can be done automatically with this function here. So if now we look at the feature data of this subset, it's smaller, and here all our markers contain a subcellular localization. Okay. So the idea is the following, is now to do some hierarchical clustering, not on the columns, not on the samples, but on the rows. The function, the code is exactly the same. We need to calculate distances and hierarchical clustering. But very often, when we do this, we get these trees that don't mean anything. I mean, they're just too big, too many features. So before doing this, we're going to transform to process our data. And really what we are interested in here is to do a hierarchical tree, not of all the proteins, but of all the proteins that belong to the endosome, all the proteins that belong to the plasma membrane, those that belong to the mitochondria. So this data set looks like this, where we have the expression matrix. And then here we have the featured metadata. And one of these columns, that is called markers, contains the information about the subcellular localization. And so they are not next to each other, but here I'm going to draw them. So here is one class, let's say the black class, here's the white class, here's the stripy class, and here's the dotted class. And what we would like to find out is something like this, for example, where we have an average measurement of all the proteins that are in the black class, an average measurement of all the proteins that are in the white class, and an average profile of all those that are in the striped class and interdotted class. Instead of having a very complex tree with 1,000 proteins, we want to summarize the protein intensities based on the classes that we have defined here. And we would do exactly the same thing if we had annotation for the samples, but then we would take averages by columns and not by rows. Okay? So let me. So EXPRS here will give you. I'm going to show only the 10 first rows, 4 first columns. So the actual data that you need to feed into distance we can get here, and the grouping you can get with dollar markers. And let me display this as a table. And here, I don't know why my art returns these messages. But here's the table. We have 25 proteins that are localized to the 40S, 43 to the 60S, 13 to the actin. But instead of having a dendrogram with these 27, 43, 16 proteins, we would like to have a dendrogram with 40S, 60S actin, and 40S should be a kind of a mean profile of these 27 proteins, of these 43 proteins, and so on. Okay. Is the question clear? Here is an example of an output that you could get. You don't need to do the coloring, but this tree is based on an average profile for 60S, 40S. And this shows the relationship between quantitation information for these proteins based on the subcellular localization. Which one?
The function marker.
No, it's actually a function for a package called prolog. And the idea here is to remove everything that is unknown for one feature variable. And it does lots of things, but here the default value is to say, look at the markers feature variable and only keep those that are not unknown. If we did not do this, here we would have an additional branch leading to a class that is called unknown. But these unknown proteins do not form an actual group of proteins. It's just the proteins that we don't know where they are. And a substantial amount of these proteins, of these 4 chapters in proteins, probably 1,000 or 2,000 belong to one of these groups. So there is no coherent signal in all those that are called unknown. Calculating an average of all these profiles meaningless. So it's better to remove them and then do our analysis on a positive control.
But the function automatically chooses the column of the
Yes. So the function has a variable called fcol for feature column, and by default that one is marked. you have, oh, sorry. So to install it, you can use the BioC manager package, function install, and
Yeah, I did that, but then even that.
Requires a package called FTC, which is not, I can't find it.
Request package INET is as well.
That's the same one.
I went to it, it's on prem, and they somehow released a version which is dependent on R 3.6.
Oh,
So you kind of, for everyone who has R 3.5,
what?
they have to install an old version of it.
is there, can you find, is there an old version of GitHub somewhere?
You can get the old version.
Could you try install the package FPC to see if
It doesn't, it's not there.
it says it doesn't find
For
it?
me, because I'm apparently running an old version of mine.
Well, 3.5 is not that old.
That's not that it shouldn't be, but it's how they did it, I don't know why.
I think we are unlucky that we just. Oh yes, 3.6. Okay. Yeah. So worst thing, you could install it manually.
So I went into, with remotes, you can install version and
Yeah.
just do one older version. But
And that works on CRAN. You can
Yes.
specify on CRAN.
it did, but there was some issues then installing further dependencies, but in the end it worked. So yeah,
Okay.
I don't know if it worked.
And we need that for the kernel package. Okay. Let's do that. Remotes.
So remotes is just what dev tools use.
So did you? I imagine you used install from DevTools.
It's basically what dev tools uses. Remotes is just
Yes, but how do?
so there you install the underscore version, then this FPC.
Install underscore version.
Yeah. And I have to just check which version. Is it not there? You use the double quote. No, you have to, I guess you have to install remotes. It's a really small package which is used.
Yeah, it should be installed because it's required by policy manager. Okay. Okay, let's proceed. I don't think we're going to try to install these packages, these dependencies one by one. Sorry about that. I'm going to show you my suggestions for this exercise, and then we'll move on and use another one. Use another one for the next part. So we could also do this with dplyr and convert the MSN set to a data set, and then gather it into a long data set. But what I did here is that I used the by function. So X is my quantitative matrix. It's this one. And then F data HLM markers is this vector. And by is going to do what group by does, maybe in a slightly less elegant manner, and that it's going to split this matrix based on the groups that are defined in that vector. And then it's going to apply one function to all of these subparts and in this case it's column mean. So I'm going to take all the proteins that correspond to this one group, and I'm going to call mean, which means I'm going to get a new vector where each value is the mean of all the proteins that belong to that group. So instead of starting with a matrix with several profiles per group, I will end up with one single profile per group here. And then I combine all these column mean profiles into a new X, which is now a new matrix, but I have one row per organelle, and then I calculate my distance, clustering, and I plot it to obtain this result. And the coloring can be done with a package called extend that extends the functionality for dendrograms, as I showed you. So let's move on to the k-means clustering, and then we'll do an exercise with another data set. So k-means clustering works like this in R. We call the k-means function on a matrix of values. Okay, so this must be a matrix that only contains quantitative values. And we need to define how many clusters we expect to find in our data set. That's, of course, a major limitation here of k-means or any clustering algorithm, is that we need to know how many clusters what we are looking at. So that's the interface or the signature of the k-means. And here's how k-means works. So I create random data. That is where I expect to find 3 clusters. So here's my data. It's 2-dimensional data. I have, I don't remember how many points, 100 points that are all supposed to belong to 3 groups. So how does k-means clustering work? So here we are. We start with this data set. And at the initialization step, each point gets assigned one of our n groups or k groups at random. So if these are the data sets, if these are the points, this point gets group black, this one green, this one red, but that's absolutely random. So that's the initialization step. And then the algorithm is going to iterate through the following steps. So the first thing is to calculate the center of all my black, all my red, and all my green points. And these centers are represented here by a full black, red, and green point. And then what the algorithm is going to do is it's going to reclassify the points based on their distance to the centers of the 3 clusters. So here, if we do this, all the points here get green, all the points there get red, and all the points there get black. And then we repeat this step, where we repeat this step, the new centers of our black, red, and green points, and we reassign the clustering based on the distance of the point to this new center. And this is repeated as several times until the algorithm converges. So here's a representation of this iteration step on a different data set, where we see that at each iteration, the centers are recalculated, recalibrated, and then, of course, the points that are close to the centers don't change, but the points that are at the boundaries between 2 clusters get reassigned every time. So that's how k-means clustering works. And there is no guarantee that k-means clustering will give us an optimal result. This will depend on this very first initialization step. Here, that is random. So different starting points might give you slightly different results. And that's why k-means is generally repeated a certain number of times. The number of times it's repeated is defined here by this n-start parameter. Okay. So we calculate here with this value we calculate, we do the analysis to cluster 10 times. We wait until each of these, that's very fast, each of these converges, and then we're going to calculate the sum of within cluster distances. So we're going to take all distances between points and the center of their cluster, take to square these distances and sum these, and then sum all these values for all the clusters. And among the 10 iterations, or the 10 parallel k-means clustering, the one that gives us the smallest objective function, the smallest total sum of squares, will be the one that is considered the best clustering. But again, there is no guarantee that this gives us the absolute best clustering. So given that you don't have the HLM data, I'm going to show here. So this works if we know the number of clusters. Okay. So for example, this code defines that we want 3 clusters. But the real difficult question here is, well, how do we know whether 3 is an appropriate number of clusters to search for in this data set? And that's arguably the most difficult question in clustering. So we have k-means clustering, hierarchical clustering, you can use different distance methods. And then there is no easy way to answer what clustering methods should we use, what the parameters are that we should use. But all these are relatively easy compared to the real difficult question is how many clusters to find. And so there are more sophisticated methods that are, as part of the clustering, will try to estimate the number of clusters that they need to find. But these are very often kind of ad hoc, developed for specific types of data sets. And the best thing is to start with simple methods like k-means. And how can we get an idea of what number of clusters, not the actual real number of clusters, but get an idea of what number of clusters to observe. And so to do that, we can write a couple of lines of code to give us a pretty good idea of what's a ballpark for the number of clusters. So let's imagine for this the data set that we used before with the localization, that, by the way, I think had 14 classes. Let's have a quick look. Yes, so 14 classes. Again, that's not but we expect to find around 14 groups in this data set. So we define here, well, let's see, we're going to test between 5 and 20 values of k, for k-means clustering, the number of clusters we need to see. So here I extract my quantitation value, and so here's what we are going to do for each of these values, 5, 6, 7, 8, 9, up to 12. Okay. For each of these values in ks, 5 to 20, sorry, we're going to perform in k-means clustering. So this is our input data. That's the current value of k. First time will be 5, second time will be 6, and so on. And we're going to repeat this 10 times. I think that's probably the default value. And every time we compute our clustering, we are going to extract this total within squared sum of distances for this cluster, which tells us, does it do a good job? Small within SS is a good clustering because we have dense clusters. And so we're going to do this for all the k's that we envision, and then we're going to plot these here. Okay, so this is the line of code that is going to produce this plot. So the total within squared distances, this is our objective function, and what we want to have is a small within SS. And so if we have only 5 clusters, we see that we do a really poor job. And indeed, the more clusters we add, the smaller our objective function becomes. Okay. And we always expect to see a graph that, a curve that becomes smaller and then slowly, asymptotically goes towards 0. Okay. And indeed, the more clusters we have, the tighter the increase will be. But on the other hand, it becomes meaningless if you have 1,000 points to say we have 1,000 clusters. So having too many clusters is a measurement of complexity of our model. Having overly complex models, or called overfitting, is not useful. So we need to find a place where this curve starts to tend towards 0 and stops diminishing. And so here, I think the real number of clusters is around 14, 15. So here, there is another drop here, but that's probably, I don't know, maybe some kind of weird effect of that iteration. So looking at this plot can give you an idea that the number of clusters to be observed is probably around 14, 15. So it's a very simple method, and there is no guarantee that it will, well, it won't give you the actual result. We will not be able to say whether it's kind of 14 where it hits down and then starts to plateau, or 15, but at least it gives us a really good idea. And let's not forget that these clusters here are very often a representation of our understanding. Right? These are quantitative data. There is no guarantee that these data that contain a lot of noise will actually perfectly cluster into a certain number of clusters. We always have points that are a little bit noisy in between. But this will give us a good idea. So I have another exercise for you that will reuse. Let me see what's. Yes, I think it's rather interesting. Again, it comes from a real-life data analysis using this small V data set again. So we have 2,337 proteins, and we have what was it? 6 time points in triplicates. And so what we would like to do, so this is a time course, we would like to get a figure like this. And here, I think I used 16 clusters. I don't remember. Okay, setting 20 clusters. And to get a figure like this, so I would want to cluster our time course data. Again, we don't know whether it's really 16 clusters that we expect to see, and clearly the difference between cluster 5 and cluster 6, I'm not sure if it's relevant. Maybe here we have a slight increase. Yeah, we have a slight increase in the Zen. Here we have a slight decrease in the 3 last figures. But we would like to see what kind of patterns do we have in this temporal gene expression figure. Okay, so here we have upregulation at the end, but not very much happening during our during the time course, and then it goes down. So trying to identify kind of pattern of gene expression that, of course, afterwards could be useful or are used for downstream analysis. So here are the set of steps that you might want to do. And so the data isn't in the Zen set, but to produce this figure with but I think I forgot to mention something here. One important piece of information that you need. So let's see, 20 clusters. Yeah. Okay. Cluster will give you the result. And it will tell you that this protein belongs to cluster 17, this one belongs to cluster 17, and so on. Okay, so within this k-means clustering, the cluster slot or element will give you the cluster attributions.
In the figure that you showed now, the y-axis was all the genes that were expressed with that particular pattern, that it thinks that it was expressed in that particular pattern.
So this is the expression intensity, and each line here represents, each colored line represents the expression pattern of one gene, and then the black one is actually, I think it's a geom smooth.
Mean of all the expressions.
Yes, exactly. So something a little bit like we did there, but done with automatically with ggplot, with a geom smooth, I think. But so basically, these are all the proteins presented here are those that cluster, that are part of cluster 9. These numbers is completely arbitrary. And the clusters have been obtained with k-mean, and then table of this, table km cluster. Okay, this tells us that I have 14 protein that belong to cluster 1, 58 that belong to cluster 2, and 10 that belong to cluster 17, and here are these 17, some of these 17 proteins. So this information, that is the result of the k-means clustering. So again, we will use k-means clustering not as a means on its own, but to calculate cluster affiliation or attribution of these proteins. And this is now something that we are going to reuse to plot our profiles, but to group our profiles based on on the results of our clustering. Yes.
So, we have multiple iterations because this algorithm depends on initialized value of the sectors. So we do it multiple times, say in this case 10 times. So how do this R function combines all the results from the
It takes the best one. It takes the best one based on the within square distances. Exactly like we did here. So here we choose the value of k based on this, the minimization of this value, given that we don't want to overfit our model, and it does the same thing. It runs it 10 times. Actually, within each of these points, it ran it, let's check. Yes, it ran it 10 times, and then it actually reported to 1.
okay, within sum of squares for that particular layer of those points.
Yes, and then it returns the actual result that minimizes this value. That's the one that we get out of k-means. And so if we look at here, assuming that there is some, even if there is no clustering structures, the differences should be relatively minimal, right? So here are certain, okay, in the beginning of iterations there is a big change, but when we look here, now the changes at every iteration become quite minimal. So we don't expect to have perfect results when we do clustering, because there is no reason why our actual biological data should cluster. You know, clustering is something that we made up. You know, it's a kind of mathematical operation that clever people came up with because they want to put some order in the data. But there is no reason why the proteins should cluster perfectly. Roughly, we will see some patterns, but some proteins that are between or uncertain, it's maybe a bit futile to want to assign it exactly a cluster. And so that maybe the next step would be to do some probabilistic clustering, where instead of saying, oh, U protein on cluster 1, U protein on cluster 2, well, maybe the first protein would have 99% probability of belonging to cluster 1 and 1% probability to belong to another cluster. Like that. And then some proteins might be 30% in one cluster, 30% in another cluster, 30% in another cluster, and then 10% in other clusters. And that is probably what is revealing, or it's, I don't know, it's data, or it's revealing interesting biology. Yes?
Trying to find the optimum amount of clusters seems like a pretty standard operation. Is there some way?
Oh,
I mean,
it is
not
the-
a standard thing to try to do.
Oh, yeah, so there are other methods, except the one that I showed you. There are other information criteria that can be used to estimate it. And so is there a function that does it out of the box? There surely is, but I can't think on the top of my head. But again, expecting to have one answer is probably unreasonable for a biological point, unless we have a synthetic data set. Very often, I think it's probably unreasonable to expect one, and it's a very hard problem. And so maybe that's why there is no kind of standard package that everybody uses, because it will be dependent on your data, the noise in your data, and the actual biology that you want to identify. Very often when these methods identify the number of clusters automatically, they become rather advanced. There is a specific modeling that happens behind the scenes with Bayesian statistics that are implemented for that very specific problem, and then they might estimate these values automatically. But that's very often an actual tool that has lots of background or underlying methods under the hood. More difficult to tackle. And so the first thing to do is to use plain k-means, get an idea, a rough estimation of the number of clusters, and see how k-means performs before moving on to more difficult. Okay, so maybe we can walk through one possibility to solve this. On screen here, so I start by calculating k-means clustering. I extract my quantitative information. Here I go for 16 clusters, 10 iterations, and the maximum number. So I restart my algorithm 10 times, and here the maximum number of iterations is 50. I think this max iter, iter max value is probably the default. It's probably fine in case the algorithm doesn't converge. And so here I use a helper function. It's going to be large. So x 1, 2, 4. To extract my data from my Zen set. So here I have my quantitative information, but this f called equals accession here tells me that I also want to have my protein accession added into this output. And then I also add here the result of my clustering. So CL cluster is going to extract for all these proteins in that same order to what clusters they were assigned to. So here it is. So these are arbitrary numbers. The fact that this one is called 9 and this one 10. These are simply values from 1 to 16 because I asked to have 16 clusters. And then here I now gather my data. Oh, interesting. So now class TB is still a data frame. Aha. Okay. That's weird. Oh, it's not weird. It's different than what we had this morning. Somebody asked me a question in one of the exercises I had. S underscore Tibble. And this was not, I don't remember who was actually. This was, yes, this was not necessary because Gatto in that case returned, although it had a data frame as it returned Tibble, and apparently here this is not the case. So sometimes it does it, sometimes it does not. I guess that's what makes using R interesting, right? And so I convert this table into a long format where I have my accession, my cluster number, my sample, and my expression. And then here I do some checks that my number of rows, making sure it didn't mess up my gathering. Okay, so that the number of rows in this table here is the same as the number of rows times the number of columns in this data set. I'm just checking that what shouldn't be necessary. Okay, and so here I extract some metadata from my object, the one that we saw before with my my time points, my replicates. There are actually now more modern functions in MSN-based that should do this automatically, but now I add all this information to my tibble. Here it is. So time point and my replicates. And now I can use ggplot2 to probably take some time. Yes. So here's the data that I want to plot. On my axis, I want to have, here I paste the time and the replicate. My expression values here at the y-axis. And then this is something that we haven't seen in ggplot yesterday and either last week, but we want to do some grouping. Okay. So we have values here along the x-axis, and we want to make sure that we get one line that is composed of all the values for based on our accession numbers. So group accession makes sure that we actually have a proper line per protein. And here I want to do clustering, coloring based on my cluster number, but here I have to specify as factor, because these cluster numbers are 1 to 16, and that looks like a quantitative value, and I don't want my colors to go from, I don't know, light blue to dark blue. I want to be these different categories, so here I use that factor. And then it's a geom line, and then wrapping based on faceted based on the cluster. And then here I add, so I have my K means clustering plot, and here I add a stat summaries where I take the mean value to add. I didn't use the geom smooth, maybe that would work too, but here I take the mean profile that I add here. That's kind of a mean cluster profile. So another technique that is used very, very often is a principal component analysis, or more generally dimensionality reduction techniques. And they are used to kind of simplify our data to go from large number of dimensions to a reduced number of dimension to facilitate, to help visualization. But they're also often used as a pre-processing method. Okay. So if we have many, many features, or too many features, we might want to run principal component analysis and only take the first set of features as an input for our second algorithm. And so how it works here is some data that I generated, and here it's two-dimensional data. So obviously we would need to do a PCA analysis if it was two-dimensional, because we cannot really visualize it, but at least it helps us to see what PCA does. So two-dimensional data, x and y. And so if we run a principal component analysis here, we start with the two-dimensional data, and we will obtain two dimensions, PC1 and PC2. And these dimensions, or the first one is a These dimensions are linear, orthogonal linear combinations of our original dimensions. And these are chosen so as to maximize the variability of the data. So the amount of variability in my original data space along x is that much, along y is that much, but PC1 is chosen so as to maximize the variability along this new dimension. And then PC2 would be orthogonal here, but would explain very little, all the residual variability, which is not very much. And then these data are kind of replotted into these new dimensions. So here, PC1 and PC2. And this is how the data looks like. Now we have to be very careful because most of the variability is explained here on PC1. So actually the way we should plot this figure is more like a rectangle. Okay, we can calculate and see later what's the percentage of variability explained, but this figure should actually be stretched because there is much more variability explained along PC1 than along PC2. And so how do we do that in R? We use the PRCon function that takes as input quantitative data. So here I can store it as PCA. So this is how we can calculate our PCA manually. And if we look at the summary here, we see the proportion of variance explained on the first PC, so 73%, 16% explained on PC2, 2% on PC3, and here's my cumulative proportions thereof. Okay, so after 5 principal components, I have over 95% of my global variability in the data. So we can plot these objects. So this is a scree plot that explains how much variance I have in my respective principal components. So clearly, if here I have a more or less uniform, it wouldn't be uniform, but not such a striking pattern, PCA would not be the most useful function. And then out of the box visualization, the Y plot. Not very beautiful. It takes a bit of time to display. Okay, following me, I'll switch on the slides. Here's the Y plot. So the actual points are our, so this is the multi-data set, the time course. Here we have the 72 hours, here we have the Zen points and 0 and so on. But in addition to that, what Biplot does is that it adds the loadings. So kind of the influence of the individual proteins that we had, and they, in this case, kind of overlay everything. So that's the default of Biplot. But very often what we are interested in doing is to extract these the new coordinates of our data points in PC space. And this is something, So here what I did is I clustered the features based on the samples. To obtain the other way around, I would need to transpose this.
Why are you translating now?
Well, it depends. Do I want to have, when I do my PCA plot, what is my question? What am I interested in? Am I interested in getting, producing the PCA plot from my samples? Okay, and then I had 72 hours somewhere here, and then I had 0 and 60 somewhere here, and then probably 24 So this is one application of my PCA plot, where I want to have my columns in PCA space. But I might want to do something else. I might be interested in this figure, which is a PCA plot, but each point here does not represent one sample, but represents one protein. And so, because these are completely different scientific questions, here I might want to do what we did before with the hierarchical clustering and see to what extent does the structure of my data correspond to my experimental design. So I want to do a grouping, clustering PCA of my samples. And this here each point represents one protein, and the different colors represent these subcellular locations that we had before, where we also did a hierarchical clustering. And here in PCA space, we see that we get a kind of nice clustering of the proteins, or grouping of the proteins based on their subcellular localization. And so my T here was to say, well, I want to transpose, because either I want to do a PCA along my samples or columns, or I don't want to do a PCA along my features or my rows. So ready to plot to update. So here it is. Where I have my samples, and so in this PCA object, I can take slot X. Let's look at this. This will give me the values, so the position for my samples on PC1, PC2, PC3. So if I yes. So if I want now to reproduce my PCA plot and not necessarily rely on this horrible biplot, and for example, I want to regenerate it with ggplot2, or I want to reuse these values as an input for another visualization, then I can access this with PCA.x. Okay, so the x being the element of the PCA object that was created with a PR column. And this is the quantitative matrix. Okay, so it's time for lunch, so we're going to stop now. And we have another session